Good morning. We present our work Detection of Events in Ringebu and Heddal stave churches using clustering and other methods. Starting from temperature and relative humidity measurements of Ringebu stave church, as the title says, the aim of our work is to find an algorithm capable of distinguishing days with any kind of event within the church from normal days. Then we check the effectiveness of the algorithm on Heddal church data. In the following, after a brief description of the dataset we used for our analysis, we present the results we get by exploiting an unsupervised learning algorithm, the density peak clustering by Alex Rodriguez and Alessandro Laio on our data. Then, we present the results of a couple of techniques of supervised learning, the application of convolutional neural networks for time series classification, and a self-made technique we called unexpected mixing ratio peaks method. At the end, we come with the conclusions. So, let's begin with the dataset presentation. We analyze the temperature and relative humidity time series in a time window that goes from March 2019 to March 2020. The data were provided by 3 data loggers as reported in the table. The first 2 sensors are inside the church and measure temperature and relative humidity with a frequency of 1 measurement every 5 minutes, while the third one is located on the outside of the church and measures the same quantities with a frequency of 1 measurement every 15 minutes. From the temperature and relative humidity time series, it is also possible to compute another important quantity, the mixing ratio. The mixing ratio combines information from relative humidity and temperature, giving an estimate of the number of water grams per kilogram of air, and it is a great indicator of the presence of people inside the church. Alongside the data were available to us also some metadata, giving some information about days with events, as it is possible to see from the blue table. In particular, we had information also about the heating system. Concerning the heating, it is important to stress the fact that the 2 churches are managed in a different way. While in Heddal stave church the heating is always on during the whole autumn-winter period, in Ringebu it is switched on only in the days with some scheduled event. The effect of the heating system on Ringebu stave church are shown in the graph below. Now that the dataset have been described, we can present the results we get from the density peak algorithm on Ringebu stave church. In this slide, it is possible to see the variables we used in order to perform the clustering. Here, there are the results of the clustering. We get a normalized mutual information of 0.395, a precision of 0.833, and a recall of 0.615.
As we have already seen, the clustering algorithm is able to find the days with events in the case of Ringebu Church. So we have tried to use the same ideas and the same criteria in a different church, in particular the Heddal Church in Norway. Here we can see the result. In this image we can see that there are just 2 main huge clusters, which is not what we would like to obtain. In particular, if we look at the NMI, we can see that it is just 0.09, which is not a good result, and also the precision is not enough, 0.16. The recall is high, but it is just due to the fact that the clusters are very huge. To understand why the clustering algorithm doesn't work in the case of the Heddal Church, we have tried to perform another analysis with the Ringebu dataset. So we've built 2 different datasets, one without the information about temperature and one with the information about temperature. In the first one, we've obtained an NMI of 0.07. In the second one, the dataset with the temperature, an NMI of 0.3, which is a huge improvement. This means that the information about the regulation of the heating inside the church, which is different between Heddal and Ringebu, is a crucial information, which perform a good clusterization in the case of Ringebu and a bad clusterization in the case of Heddal. Also here, if we look at these graphs, we can see that in the case without temperature, there is not a particular structure which is easy to clusterize. But if we look at that dataset with the temperature, we can see that there is an area which is easy to clusterize. Also, if we look at the dataset without the temperature, but looking at the true labels, we can see that the clusterization is completely wrong and difficult. Then, if we look at the graph of the dataset with the temperature, we can see that there's an area with a lot of true labels, but there are still some points which are outside. Those points are the points that belong to the spring and summer seasons, which are difficult to classify because these days, if we look at the dataset, are very difficult to distinguish between the inside and the outside of the church as regards humidity, as regards mixing ratio, and as regards the temperature. This means that we cannot use it to classify well. Because of these problems, we've tried also different methods other than the clusterization technique.
At this point, we have tried a supervised learning approach, in particular a convolutional neural network for one-dimensional time series classification, using the internal mixing ratio. Firstly, we manipulate our data in 3 steps. We compute the average between the 2 sensors, then we smooth the curves, and we reduce them taking a sample every 4. We also operate a mirror augmentation where all the series are mirrored, reversing the order of all the values. It is important to know that this augmentation is made only the days with events. This is our architecture. Starting from the left, we can see the input layer, then a first convolutional layer followed by a max pooling. Then there is another convolutional layer and a global max pooling. Finally, we have the flattened and 2 dense layers. In this table, we can see all the settings of our architecture. We can note that the size of the training set after the augmentation is only 492, and this is not a good number to train a CNN. Indeed, this leads to unstable results. The results depend also on the splitting of the training set, and to avoid this second problem, we have operated a K4 cross-validation with key equal to 5. These are the results for one run. We see the wide range of the normalized mutual information, and after many runs, the results are more stable, but we have not really good performances. So we have decided to use a new supervised learning approach that we called UMR Peak method. UMR stands for Unexpected Mixing Ratio Peak, and it is composed by 2 main steps. Firstly, we manipulate the mixing ratio series to extract one feature for each day, and then we operate a binary classification with 1 parameter. The manipulation follows an heuristic assumption. Days with events are characterized by at least one internal mixing ratio peak, not explained by an external mixing ratio peak. Using the 3 mixing ratio series, we compute the average between the 2 internal sensors, and then we smoothed the series. For the internal one, we take an average window of 7 samples, and for the external, we take a window of 21 samples, before and after the one considered. Now, we compute the first discrete derivative with a discretization step of 5 minutes. Starting from the derivatives, we compute their maximum and minimum with some constraints. The minimum is always after the corresponding maximum of the external quantities happen before the internal one. So, for example, we want the minimum of the derivative of the external mixing ratio before the minimum of the derivative of the internal mixing ratio and after the maximum of the external one. Finally, we can compute now with all these 4 values for each day our future that we call delta. Delta is defined as we can see in this slide.
Now that we have seen how to compute our feature delta, let's see the UMR Peak method result. Starting from a visualization, here we can see the value of delta for each day and for both charges, and in particular we can see how there is a good separation between days with label 1, so with events, and days with label 0, so without events. This is true except for Ringebu summer, let's say, where things are more confused maybe because of dry weather or open windows, which make more difficult to detect events. Here we can see the same plot, but not with label 0 of 1, but with the number of people that visit the churches, and we can see that there is a relation between the value of delta and the number of people. Now the idea of the classification is very simple. So in particular, if a day has a value of delta greater than a threshold, this day is labeled with 1, so as a day with events, and then the delta threshold is optimized, maximizing the normalized mutual information. Here we can see the results, so in particular precision, recall, and NMI for both churches with respect to the value of the threshold, and below the graph we can see the best results. So performances are not incredible, but the interesting thing is that they are very similar for both churches, so this method seems to have a good repeatability. Now, a strange thing is that there are days with true label 0, but with a very high value of delta. So how can we explain it? If we go and check the mixing ratio measurements of those days, we can see, for example, for the Ringebu days, that there is the heating curve, so mixing ratio slowly go up and then down, but around 11-12 am there are huge peak on the internal mixing ratio, and this is very likely due to a celebration. While for the Heddal day number 171 is very difficult to just by sight, and in the day 311 we can see there is an error in the measurement of the first internal sensor. So now go to the conclusions. Here there is a tab with a recap of the performances of our methods and their limitations. So clustering recognize heating and not event with people. The CNN has very unstable results because of the small number of variable data. And finally, the UMR Peak method is solid, allow us to find the days with wrong label or with error in the measurements, but it is based on an arbitrary data manipulation. So this ends our presentation, and here we can see our team. Thank you for your kind attention.